Hi everyone, I'm Mengyun Zhou from Fudan University. Today, I'm going to introduce our system, Flex HTTP, an intelligent and scalable HTTP version selection system. This is a joint work with Zheng, Shihan, Xin, and Yang from Fudan University. In the past 2 years, the work from home scenario has begun to emerge because of the COVID-19. People's demand for a high-quality network burst out. So, optimizing internet traffic has been more important than ever before. At the same time, with the growth of mobile application usage, users expect a fast and smooth experience with online services. However, HTTP 1.1, the main HTTP version dominated for decades, has too many inherent shortcomings and is hardly to satisfy these demands. Recently, some new improvements have been proposed to achieve a better experience on web browsing. These approaches can be divided into separate ways. The first approach is based on TCP. It adopts the BBR conjunction algorithm, TLS 1.2, and Speedy Protocol, which finally become the HTTP 2. H2 is a milestone and brings many optimizations, such as multiplexing, server push, and string prioritization. H2 enhances H1.1 and makes the data transmission more efficient. Another approach is based on UDP. In 2015, Google proposed QUIC on the top of UDP to replace the TCP with a new reliable protocol. HTTP3 is known as HTTP over QUIC, since it uses the QUIC protocol for data transmission. H3 improves the quality of service by reducing connection and transmission delays. Although both H2 and H3 promise to improve the web browsing, there is still a question for which HTTP version performs better and will be the next mainstream. So, to study this critical problem, we start with a series of measurements for H2 and H3 on the Emulab testbed, and find that neither H2 nor H3 can always achieve bad performance. Here, we plot the performance comparison of H2 and H3 under different network conditions and web page structures. Well, blue means H2 is better, while red means H3 is better. We found that both network conditions and web page structures will affect the comparison of two HTTP versions' performance. From the perspective of network conditions, H3 displays advantages over H2 in poor network conditions with high latency and high packet loss rate. While for web page structures, a few small files can help H2 be better than H3. This phenomenon brings another question. Could the HTTP version be automatically selected to achieve a bad performance? The answer is yes. Here, we propose our system, Flex HTTP. Flex HTTP equips a supervised machine learning-based classifier in the browser as a plug-in, and make flexible HTTP version selections before each browsing according to current network conditions and web page structures. However, we face two challenges when designing and implementing Flex HTTP. The first challenge is how to reduce the network condition measurement overhead. The classifier requires information on network conditions and web page structure as input for making HTTP version selections. However, the network condition feature is link-based, which means one link corresponds to one network condition. So, given a large number of clients and web servers, the possible number of client-server pairs and the corresponding features would be huge. Such real-time network measurements will introduce a significant amount of traffic overhead. The second challenge is the classifier updating mechanism design. Network conditions are constantly fluctuating, so an immutable classifier might be out of date after a period of time and make a wrong HTTP version selection. So we should periodically update the classifier. However, the better-designed update mechanism could destroy the performance of classifier. The timeliness and the generality are two requirements when updating the classifier. Okay, so now let's see how Flex HTTP solves the first challenge, how to reduce measurement traffic to a moderate level. Here we have a client and three services. According to the previous principle of one link, one network condition, this client needs to measure the network conditions of the three services respectively. Then we observe an interesting phenomenon. The three network conditions are similar. We traceroute these services and found that the three services are from the same region. This phenomenon inspires us. Could we use a representative agent to aggregate network conditions? So, in Flex HTTP, we deploy an agent server to aggregate the network conditions by representing the group of nearby web services in the same region. So, instead of measuring the network conditions to these services respectively, the client can do measurement to the agent server. Then, the measured value from the agent server can represent the network condition of all services in the same region. Such aggregation reduces the measurement traffic to a moderate level. We believe that agent servers could achieve a reasonable approximation to represent nearby web servers, because most of the services are deployed in closed data centers. Similarly, if the client wants to access other regions' network conditions, it can obtain the network conditions from the agent servers located in these regions. Okay, now let's see how Flex HTTP solves the second challenge, how to update the classifier with ensuring the timeliness and generality. We have two candidate update mechanisms. The first is to let the client maintain a local transport by itself, and then update the classifier on the client side. This update mechanism can guarantee high timeliness. However, only using the local transport for retraining will make the classifier underfit and perform poorly. The second is the global updating. After deploying a series of agent servers, we can let the agent servers collect traces and perform updating. Global updating can ensure the generality and the robustness of the classifier, because the classifier is built on a more comprehensive dataset. However, global updating also suffers from difficulty in matching user-specific characteristics. So, to solve this, we update the classifier by combining the local updating and global information, which brings the advantages of two update mechanisms. The hybrid global-local update mechanism works as follows. First, we introduce a local trace pool at the client side to collect the user's browsing traces and the corresponding features. But as we said before, the local traces are not enough for updating. So, the retraining process also combines the global classifier downloaded from the agent server. The global classifier is able to provide the global information because it is built on the global trace pool. Additionally, each client will periodically upload the local traces to its nearby agent servers to enrich the global trace pool. So, the three components work together to make sure the operation of the hybrid global-local update mechanism. Okay, now let's see how the end users interact with Flex HTTP. Flex HTTP works like a browser plugin. It will make an HTTP version selection before browsing. Additionally, in order to reduce repeated classifier inference under a similar situation, we add a cache mechanism. If a request does not hit the cache, Flex HTTP will randomly select a version between H2 and H3 and update the cache with the local classifier. Here, we conduct an evaluation of Flex HTTP on Emulab testbed. We use the speed index to evaluate the performance. Speed index is a metric that indicates how quickly a page is loaded and visibly rendered. First, we present Flex HTTP's potential in reducing speed index. In the left figure, compared with H2 and H3, Flex HTTP achieves less speed index values in terms of either the mean or median value. The mean speed index value of Flex HTTP is 600 milliseconds and 480 milliseconds shorter than those of H2 and H3 respectively. Furthermore, we investigate the speed index of H2, H3, and Flex HTTP on each configuration in Figure B. We found that Flex HTTP can always capture the appropriate HTTP version in almost every experiment configuration. So, in a word, Flex HTTP can select a more appropriate HTTP version to improve browsing performance. So, to conclude, our work finds that both network conditions and web page structures affect the performance of H2 and H3. And motivated by this finding, we propose Flex HTTP, a machine learning-based intelligent and scalable HTTP version selection system. The distributed agent servers and the hybrid global-local update mechanism ensure the scalability and information timeliness of Flex HTTP. And the experiment results demonstrate that Flex HTTP can choose the appropriate HTTP version to achieve a better user experience. Flex HTTP source code is available by the following GitHub link. That's the end of my talk. I will be happy to take questions.